luckily for us, Nick Direen has kindly offered to fill in for us this evening as we lost our original speaker. And I've only just met Nick very recently, so I'm getting to know him a bit more. So I'll introduce him and tell you that he's a geophysicist as well as a geologist. He's got a very extensive background. He's worked in lots of different places and lots of different settings, and I'll just try and summarise them for you. Nick's worked at AGSO, and he's been involved with Lachlan Fold Belt and Olympic Dam IOCG style deposits there with them. He also worked on the Law of the Sea project in Antarctica, focusing on seismic interp. He was also at Adelaide Uni for a while as a teacher, and he focused on tectonics and structural geology there, as well as exploration geophysics. He also worked on FrOGTech in oil exploration before moving on to Exxon and doing gravity and EM with them before moving into their centre of expertise, which I think, sorry, that was their centre of expertise, and then went on to their commercial department. And I guess now Nick's an associate. Are you an associate? What role is it? Professor?
Yeah, associate, no, researcher.
No, researcher, sorry, at UTAS. And he's also currently working for MITRE Geophysics. And tonight, one of Nick's passions is the King Island Scheelite deposit, and it looks like the rocks of King Island all over itself. So he's going to give us an update on some of the work he's been doing there and the field trips he's been conducting. So welcome, Nick. Thank you very much.
Thanks, Jane. Just before I get going, I just want to make sure that people can see my slide.
I can. So well, I can.
Okay. That's good. All right, well, let's get going then. So to introduce things, I've been working on King Island geology since about 1997 when I went there for my PhD, and it's a fascinating place. It's got a whole lot of different. Some background noise from some people.
25 July. Everyone who was there at that time is to isolate for 14 days.
Can we,
very close.
Jane, can we mute everyone else except me?
I'll just see if I can mute people. There you go.
Thank you.
All right.
Yep.
I'll see how I go.
It's all right as long as you don't mute me. Otherwise, it's going to be pretty boring talk. Mime it.
I'll mute everyone else. I'm onto it.
All right, so there's plenty of cool rocks which I'll walk you through the stratigraphy as we go through the talk. But more recently, I've become interested in the King Island Scheelite deposit, and there's two of those at least: the Dolphin deposit and the Bold Head deposits. And they're interesting at the moment because tungsten has come back in vogue as a critical mineral. I'll talk a little bit more about that. But crucially, King Island Scheelite, the company, has dewatered the old Grassy Mine, and that's opened up access to the rocks down in the mine, and they've also been doing drilling. And tonight I'll talk about some of the things that I've been looking at with the new drilling and doing some geophysics over the Grassy area and looking at maybe understanding how the Scheelite deposits form. There's already a body of work in the literature from the 50s through to the 90s, but you know, new techniques arrived while the mine was shut, so there's new things to look at now. Right. So tonight we'll try and give you a view that King Island's a really unique geological laboratory. It's got rocks from the Mesoproterozoic through to the Miocene and some Quaternary sand dunes on top of that. One of the key pieces of stratigraphy that's generated a lot of interest and a lot of international interest is the Snowball Earth sequence of rocks, and I'll show you the glacial deposits and the cap carbonate from the Grassy group, and you know, look at some of the controversies that have been generated there. But for the perspective of the mine and the generation of the Scheelite deposit, that cap carbonate, the Cumberland Creek dolomite, is a massive mineral system chemical trap, and it's really effective and has been mineralised to make these world-class skarns that exist on King Island. Above that sequence of rocks, the Snowball Earth stuff, there's also a very thick package of volcanic rocks, many kilometres of basalts, and that's the sequence that originally took me to King Island in 1997. And they form a really well-preserved Neoproterozoic volcanic margin. So I'll talk a little bit about that, but not much. It's a whole talk in itself. And then show you, some of the new drilling that's been done on the Grassy deposit and some of the geophysical work that I've been doing recently. And that's still actually a world-class resource. There's a few million tonnes of tungsten mineralisation still in the ground on King Island, and that's why King Island Shear Light's actually looking to revitalise that mine in the near future. All right, so King Island, can I just check, Jane, can you folks see my cursor, or do I need to make a special cursor? Can you see me pointing?
Yes, I can.
Okay, great. All right, so King Island is off to the northwest.
I think Jess is getting his loan in a couple of weeks.
Okay.
Still getting some background noise, so if we could just mute people, that'd be great.
They're coming in and I'm turning them off as quick as I can.
Thanks, Jane. So King Island's to the northwest of Tasmania. I don't know who's in on this talk, but I get the impression there's some mainland people. So for us, King Island's this little piece of geology up here. The two golden dots that you'll see throughout this talk are holes drilled recently by King Island Shear Light, and I'll talk about a little bit about those. The key thing to take away from here is, even though King Island's relatively close to Tasmania, there's some rocks on King Island that are not exposed anywhere else in Tasmania, particularly. But there are similarities with the Smithton Trough, which is this piece in the northwest corner of Tassie. And the things that are similar are the Smithton Trough Tagari group here is equivalent to the Grassy group sequence, which is up here on the east coast of King Island. And the volcanic rocks in that sequence are similar to the Crimson Creek Formation basalts and also the Spinks Creek basalts, which are in here. The Crimson Creek Formation, for those of you who've got your economic geology hats on, is partly the host of the Renison Bell skarn deposit. So there's some interesting sort of connections of the rocks and the ore deposits, even though Renison Bell's a tin mine and Grassy is a tungsten mine. But it's the fact that there are these thick carbonates sitting in the sequence that are particularly reactive that make these things happen later. So let's sort of walk you through the stratigraphy. I'll give a shout out to Clive Calver, who's the MRT geologist who mapped King Island for the state through the 2000s. Clive's actually giving a talk tonight in Melbourne for the Geological Society, so we've got sort of dueling King Island talks tonight. But he and I have worked pretty closely on the geology over the years and trading ideas, and sort of what I'll present tonight's a synthesis of our work. So I'm going to talk not much about the Quaternary at all. We'll talk a lot about this package of rocks here, the Grassy group, a little bit about the basement under there, the Fraser Formation, which is the Mesoproterozoic siltstone sequence. The equivalent rocks on the west coast of King Island are called the Surprise Bay Formation. They're actually the same age as these, but they're much more cooked up, and I'll show those in a minute. And then the intrusive rocks, start with the older ones, the Lorana Granite and the Cape Wickham Granite, intrude this sequence, but not that sequence. They're about 750 million years old. The intrusive rocks that feed the big volcanic package, talk a little bit about those. And then the real critical event for generating the tungsten mineralisation on King Island was the Carboniferous intrusion of this granite called the Sandblow Granite. It used to be known as the Grassy Granodiorite, and a faulted off piece of that called the Bold Head Granite, which we'll talk about as well. So in a more time series look, we've got the Quaternary sand dunes sitting over the top. This is what hosts the golf courses that are very popular on King Island today. The Bass Basin is also exposed on King Island. Not going to talk about that really at all. but it's quite a thick package, and we've got knowledge of that from drilling offshore. My previous employer, ExxonMobil, drilled a lot of holes into it, trying to find oil. None there. Critical event, 351 million years ago, intrusion of the sandblow and sea elephant granites that caused the skarn mineralisation. Most of the Paleozoic history of this part of the world is non-existent. There's just a big unconformity, and there's no rocks deposited during that time, unlike the rest of Western Tasmania, where this is all full up of exciting and mineralised things. The Cambrian orogeny that is experienced in Tasmania, the Tyanna, is not known on King Island. There's no metamorphic dates of Cambrian age, so King Island escaped that massive event, which we'll talk about a little bit more later. But what is of note on King Island is a pretty significant set of Neoproterozoic rocks, volcanics, and this glacial sequence, which we'll talk about, that's been skarned up by the intrusion of the Carboniferous granite. And then there's an older set of granites, one at the northern end of the island and one over near Curry on the west coast, about 750 million years old, intruded during something called the Wickham event. Used to be thought of perhaps as an orogenic event, but that's sort of been downplayed more recently. This looks more like a local intrusive type deformation. This stuff's only known a little bit from northwestern Tasmania, but it is also known from Antarctica. So there's an Antarctic connection with these rocks here. And then the real basement of King Island is the Fraser Formation and the Surprise Bay Formation. And they're an old series of basins that have been well and truly metamorphosed and deformed multiple times, which we'll talk about in a minute. And I'm sure I saw Paul Blackney in the Zoom meeting and say hi to Paul. Paul mapped this stuff for his honours thesis back in the day. All right, so just to kind of give a little flavour of what King Island connects to, there's been a lot of work done on the zircons from the Surprise Bay Formation and the Fraser Formation. They're related to the Rocky Cape group, which is exposed on the margins of the Smithton Trough. And those have, in fairly recent years, in the last 5 or 6 years, been connected through to Antarctica and to North America. So King Island is a little fragment of terrain that sort of doesn't really belong to the rest of Australia. It's got left behind during subsequent events and kind of attached itself to Tasmania, sort of at Cretaceous rifting time when we broke away from Antarctica. The other key sequence of rocks that correlate through to northwest Tassie, but also potentially to North America, are the Grassy group, and this is the equivalent in the Smithton Trough. Just how do we know that stuff? As I said, a lot of work being done on zircons. Clive and other authors here at UTAS have been sort of barcoding the Surprise Bay Formation, found out that it's, apart from its metamorphic grade, it's effectively the same rock package as the Fraser Formation, which is the same equivalent package to the lower Rocky Cape group. The upper Rocky Cape group, which is exposed at Boat Harbour, which has the beautiful cross-bedded sandstones, is actually a bit younger than all of the rest of this stuff. So that's there's obviously a big unconformity between the lower part of the Rocky Cape and the upper Rocky Cape, but we're not going to talk about that tonight, merely to say that King Island looks like part of northwest Tassie at that time. And this is what it looks like in the field, which I guess we'll start walking through through a series of rock columns now. So this is the Surprise Bay Formation as exposed on the west coast. It's a series of garnet and andalusite schists. So you can see the garnets and the andalusites, big knotty rocks, low pressure, high medium temperature metamorphic complex, basically. As you go to the north part of King Island, that rock set is intruded and migmatized by the Cape Wickham granites. So you can actually see pods of that formation melted into the granite up there and big sets of dikes. This is Sebastian Meffra, our current head of discipline here at UTAS, back in '97 when we first went to King Island. And as you go around just to the east of Cape Wickham itself, near the lighthouse, which is a famous landmark, the full granite is exposed. So we go from migmatites in the Surprise Bay Formation to the actual granite itself. The granite there is, unsurprisingly, an S-type granite melted out of the underlying basement. There's a porphyritic phase. There's some other sort of less porphyritic phases, and those have been dated at around 760 million years old. There's another granite of a similar age down near Curry on the west coast, and this is exposed near the Curry Jetty. It's not really looking like an S-type. This looks more like an I-type with mafic enclaves, hornblende, biotite, and so forth. So there's obviously a more complicated, older history, but we won't talk about that. This is all basement to the King Island Scheelite rocks. Moving over to the east coast, a series of rocks exposed here that I've spent a lot of time mapping and trying to get to the bottom of. So they sit unconformably on top of the Fraser Formation, which is this brown sequence over here, which is the equivalent of the Surprise Bay Formation. And I'll walk you up through this stratigraphic column. So this is the Fraser Formation exposed near Narracoopa on the east coast. Lots of fine-grained turbidites. You can find crossbeds, you can find evidence of internal deformations in these rocks. So they're a set of fine-grained turbidites, pretty well exposed and a large part of the core of King Island. Unconformably above those is the Grassy Group. And Grassy Group, as I said in the introductory comments, has attracted a lot of international attention from different scientists who've been working on the snowball Earth theory. Grassy Group and the Cotton's breccia within it was first described by Jim Jago from the University of South Australia in the 70s. Jim's a Tasmanian. Many of you probably have come across him. And it's since been investigated by quite a lot of international authors, including a group from North America, trying to correlate this unit with similar glacial activities in the Neoproterozoic at either 750 million years ago or 635 million years ago, the two snowball Earth events that sort of froze the whole Earth for a period of time. That's the theory. And this is taken from this paper by the North Americans. Cotton's breccia and the Cumberland Creek dollar stone are believed to be part of the 635 million year global glaciogenic event. Jim Jago and myself published a piece of work on the Cotton's breccia, which we'll talk about in a minute, suggesting that it's not all just glacial deposit. There's quite a few other things in there that are non-glacial in origin. And subsequent work by Clive Calver has kind of resolved some of the controversial pieces of that information. We'll get to that in a minute. The bottom part of the Grassy Group is a unit called the Robbins Creek Formation, and this is it here exposed in here to Robbins Creek. It's a series of laminated shales, but also importantly limestone units and a few basalts intermingled with it. So it's the onset of some sort of tectonic activity, possibly a lake deposit or a rift valley of some sort with a lake in it. But the key thing for formation of the grassy tungsten deposit is that this unit's got carbonates in it, so it eventually becomes mineralised. Sorry, I think I've gone the wrong way. Cotton's breccia lies above the Robbins Formation. There were debates for probably a decade or two about whether Cotton's breccia was 575 million years old, like the volcanics above it, or older, 635 million years, like all the other snowball Earth carbonate units in China and Namibia and places like that. One of the things that was against the Cotton's breccia being a glacial unit was there's no evidence in it for things in the classic type section in South Australia, evidence of grounded ice, tidal reworking, things like that. Just not seeing that, and I'll show you some of the evidence in a minute. But nevertheless, as more people have worked on the unit, it's become clear that parts of it definitely are glacial. And there was a key date done a couple of years ago by Clive Calver at the top of the breccia. I'll show you the unit in a minute. giving it a 636 million year old age. Immediately above that is the dolostone, which is important in the mine sequence. And then above that are all the volcanics. So we've got a significant time gap of about 60 million years between what is the Snowball Earth part of the Grassy group and the upper part of the Grassy group, which is full of volcanic units. All right, so here's the Cotton's breccia as exposed at Cotton's Beach on the east coast of King Island. You can see thick breccia units, but also some quite thick cross and planar laminated current bedded units. And those are interspersed throughout the breccia unit. Jim Jago and I interpreted some of this to do with slumping and rift-related activity, but definitely other parts of it are glacial. And here are some of the evidence that was acquired by Paul Hoffman, a fairly famous Harvard geologist who came to King Island in the mid-2010s and did a lot of work there. So you can see, you know, bending of bedding around drop stones that have come in from iceberg activity. Some more clasts and things in here that you can see. This is ice rain out debris, as they've called it. And then, you know, massive, quite thick, huge boulder breccias in the Cotton's breccia. One of the other curious parts of Cotton's breccia, this is from an outcrop at a place called the Gut, is that the breccia contains big boulders of breccia. This is a rather large, it's larger than Sebastian, big clast of limestone breccia with other pieces of limestone in it. And so any model for Cotton's breccia has to explain why you've got recycling of breccia within breccia units. And Jim Jago and I basically said, well, you've got, you know, limestones up here deposited in a basin. There must be active faulting. You depositing units like this in a basin, then refaulting them and sliding them down slopes, and you get breccia in breccia type activity. So Cotton's breccia is a recycled second cycle carbonate unit. It also contains one 10-metre thick volcaniclastic sandstone, which is this unit here, and this is a thin section of it. This unit, despite being 635 million years old, still contains shards of tuff, bubble wall fragments of glassy, well-preserved pumice. And this is quite astonishing that such a delicate texture could be preserved for 635 million years, but that's not surprising when I told you that this unit, all of King Island, pretty much escaped the Cambrian deformation that's well established in Tasmania, and also pretty much escaped the Devonian Tabarabaran deformation. So units like this can be preserved pretty much intact. This is the top of Cotton's breccia. Is a well-sorted carbonate class conglomerate graded up to a red sandstone, and this is the unit that gave the 636 million year age. And then directly above that, this yellowish stuff here is the Cumberland Creek dolostone, which is the cap carbonate to this glacial sequence. And this is the sort of global stratigraphic marker that all of the famous geologists have come to. And if I haven't got any great pictures here, but the east coast of King Island has had the absolute bejesus drilled out of it by people kind of investigating these units for paleomagnetic purposes. So most of the outcrops are now covered in little spot drilling things. So this is the cap carbonate. It's not a uniform unit by any means. It's 10 metres thick. The base of it is a peloidal dolostone. This is a thin section of Clive Calver's, little pelletal algal type things in a sparry matrix. The middle unit is this, and I'll show a bit more details of this in a minute. So this cross-laminated dolostone, and then above that is a marly kind of shaly limestone unit, so interbands of shale and limestone. This is Paul Hoffman clambering over the units when we first took him there in about 2009. The dolostone has hummocky cross stratification in it, some decent cross-laminated beds, and this is more details of the lenticular lamination. So for a thin dolomite unit, there was quite a bit going on, and there have been papers published about why it's got so many sort of different types of stratification in it to do with what was going on at the end of the Snowball Earth activity. Above Cumberland Creek Dollarstone is the Yarra Creek Shale, and that's also a compound unit. It's got thinly bedded grey and black shale beds that have got microbial mats in them, another one of Clive's thin sections. And then the top of Yarra Creek Shale is this red, really distinctive red shale, and at the top of it, it's interbedded with peperitic volcanics. So these little wormy green-looking things in here are basalts that have intruded into wet sediment, sort of wormed their way in under the seabed before erupting to the surface. So the Yarra Creek Shale is also an interesting unit. The very top of it shows extensional deformation as the pillow basalts were being deposited, or very soon after that. So you've got in this section here little normal faults extending the shale unit, and then right above it volcanic pillows. These have been dated. There's also feeding those volcanics and intruding into the Yarra Creek Shale, this pink unit on this cross section here. This is a manifestation of that unit here. It's a sill, highly unusual ultramafic to felsic sill, so the bases are quite rich in olivine, but the tops are rhyolites, so settled out crystals within these sill complexes. And Clive Calver and my own mapping have shown that there's distinct amount of dilation as this sill was being intruded into the Yarra Creek Shale. So part of the shale was sufficiently lithified to accommodate an intrusion, but the top of it was still unlithified, and you get those peperitic volcanic manifestations like this, which is a raft of the Yarra Creek Shale, quite cooked, sitting on a lava flow of what's called the City of Melbourne volcanics. So this is the bottom of the big volcanic pile on the east coast of King Island. There's a lot of other great volcanic textures in this unit. These are pillow lavas within a greeny altered hyaloclastite matrix, so devitrified lava glass, spalled off and shattered as these lavas were feeding in underwater. A modern analogue for that kind of thing, not in the geochemistry, but just in the physical processes. This is a lava delta on Kilauea, aerial photograph from USGS. So lava's flowing down, they hit the water, they instantly freeze, a lot of steam going off and breaking off of the lava at the front of that, and you get these hyaloclastite fan deltas sitting underwater, capped by the subaerial lava flows. So that's the sort of analogue for what we're seeing in the bottom of the volcanics on King Island. This is Michael Roach's legs. I don't know if Roachy's on the call, but this is Michael standing on one of these lava-influenced mass flow breccias. So this is an underwater deposit, big clast of all kinds of stuff. There's carbonates in these as well from the sort of underlying basement rocks as things have been actively rifting, tumbled into the basin. Bits of lava, bits of hyaloclastite and volcanic clasts all mixed up in this big chaotic lava, mass flow breccia. Just a few more pictures of the pillow lava sequence of the City of Melbourne Bay. Basically, these kind of well-preserved pillow textures mean that there was significant water depth to prevent these things sort of just exploding and disaggregating themselves. On top of that City of Melbourne volcanics, there's another volcanic unit called the shower droplet volcanics, and this has a distinctive, very ultramafic geochemistry. These are pickrite lavas rich in olivine, and they've been erupted at temperatures of up to 1100 degrees. So they're really low viscosity. They form really thin flows compared to the ones underneath them, and quite small pillows usually. This is a happy volcanologist, one of our SEG students who I went to King Island with in April, and very happy with looking at the kind of pickrite pillows, which are quite rare in the world. There's some cool volcanic textures in amongst that unit. There's evidence for subaerial eruption. So these are ropey Pahoehoe lava tops. They're red, oxidized, being erupted in the subaerial environment. So evidence at that time for sort of very active tectonics. Sometimes the lava pile was erupted in the air, sometimes in the water, depending on the balance between rifting and accommodation. There are variolites within these rocks. This is a quenching texture, so cooling from really high 1100 degrees to lava glass form these variolites, and these probably erupted in quite shallow water. This is a lapilli tuff from the shower droplet volcanics, and this is evidence of a subaerial explosive eruption. These little lapillis are like volcanic hail, gas charged, particle charged cloud from an eruption aggregates on crystals and then rains out and forms these lapillis, and then they're settled, make these kind of distinctive spotty units. Above the shower droplet volcanics, there's another quite thick unit called the Graham's Road volcanics, distinctive different chemistry to the underlying rocks. It's 1200 metres thick at least. There's 400 metres of stacked basalt flows, and then on top of that 800 metres of basalt intercalated with volcanic conglomerates in a carbonate matrix. So that's that fretted kind of carbonate sitting there with these clasts of mostly mafic volcanics, but this is a piece of rhyolite. And we've traced that unit offshore because it's quite magnetic, and there's a big magnetic anomaly off the coast of King Island, which is in this grey shaded thing here, and building a magnetic model for that sort of sequence of basalts going offshore King Island, we get to a thickness of about 5 kilometres of lava flows going offshore underneath the tertiary Bass Basin. So there's a significant volume of that stuff still sitting out here. And it's very magnetic, and it can be traced around. Talk more about that in a minute. Right, so that's the top of the grassy group, which is Neoproterozoic. And so before we get to the excitement of the Carboniferous, where all that stuff was intruded by a big granite, on mainland Tasmania, we had two significant orogenies before including the Devonian one. The first is the Tyanna Neurogen in the Cambrian, and this is a model for that fairly recently published by Jack Mulder, who's now at Monash Uni, showing, the sort of internal Cambrian core, the Tyannan region of Tasmania, which is multiply deformed, and these slices of imbricated serpentinites and bits and pieces of Cambrian and Neoproterozoic sediments like the Una Formation and the Rocky Cape group all stacked up over here. And on this map, it says to King Island. King Island's in the autochthonous zone, according to this model. King Island would be out over here. So it didn't suffer any of this multiple deformation in the Cambrian, nor any of this significant thrusting that we see on mainland Tasmania. So hence we can preserve older rock packages without significant metamorphic effects. In the Devonian, this is Tasmania here. King Island is under this dot. Tasmania was generally part of a sort of circum-Gondwana orogenic belt, which had a lot of intrusions into it. These are big granite complexes. Eastern Tasmania is full of granite. Western Tasmania's got a lot of granites, like the ones that form Renison Bell. But the Devonian on King Island, there's no evidence that potassium argon isotopes were reset on King Island. So there's 750 million year old granites that don't have any disturbance to their isotope systems from the Devonian event, and that's been pretty well studied by some experts. So that means King Island, whatever it was doing in the Devonian, was not really caught up in the significant compressional orogenesis that was going on in Gondwana at the time. And so the granite on King Island is post-orogenic, and that's some work by Dave Cook and his students. So this is the Sandblow Granite, the granite that does all the juicing up of the sequence in the grassy group. Carboniferous in age. It's got some pretty cool megacrystic textures in places, big K-spars, one's at least 10, 12 centimetres long. It's an I-type granite. It's got magnetite hornblende sphene in it. Different, very different to the ones on the north coast, Cape Wickham granite and the Lorana granite, which are more S-type. This one's got mafic enclaves, and this is a fairly classic exposure just near Grassy Harbour. In the literature, sorry, if you go back to the literature from the mine in the 70s, 80s, and even to the 90s, this unit was being called the Grassy Granodiorite. Clive Calver renamed it to kind of avoid confusion with the Grassy group, which had the sort of stratigraphic nomenclature priority. This is the Grassy Mine in 2009, when I led a field trip to the island for the GSA Tasmania, and at that point the mine was flooded, so you couldn't actually get into the mine very much at all. So it wasn't accessible. Just kind of a side note here, the current resource, or not the current resource, but the recognised resource in the mine still has 17 million tonnes at nearly 1% tungsten oxide. So that's still actually a world-class ore body according to current grades of tungsten that are being mined in the world today. Unfortunately, of course, it was flooded, so it had to be dewatered before anything else, and that's what King Island Scheelite have been doing the last few years. Just as an aside, what is tungsten used for? We used to hear a lot about it in light globes, because it formed the electric filament of incandescent globes, but they've gone out of fashion these days. So what's tungsten currently used for? The key to its use currently is the fact it's really stable and really dense. It has the same density as gold, so over 19 grams per cubic centimetre. But unlike gold, it has a really, really high melting point, over 3,000 degrees. So, and it's conductive, of course. So you can use tungsten in things where you need a high heat capacity for stuff that won't melt. So high heat electronics, things in smartphones where there's a lot of heat in a small area, heat sinks, cathode ray tubes, which is still in use. Because it's so dense and heavy, you can use it in small elliptical motors. So in your mobile phone, the little thing that vibrates has a piece of tungsten in it. It's a little dense flywheel, basically. Tungsten's also used in a variety of other things, arc furnace elements, corrosion-resistant seals in oil and gas pipes, tungsten carbide drill bits for high heat things, and military usages. And I've got a sort of footnote down here. If you want a very cool demonstration of how much tungsten is in an iPhone, and also what other elements are in your iPhone, go and have a look at this video of scientists shredding an iPhone, which I highly recommend as entertaining. One of the key outcomes of that piece of research, it's not just trivia, is that iPhones themselves demand over 1,000 tonnes of tungsten to be mined per year just to keep those phones in our pockets. All right, so this is the Grassy Open Cut this year. There's still a small lake in the bottom, but you can see the pipes in here going up out of the mine to get rid of the water. This is the portal for the Dolphin mine. So this is the Grassy Open Cut, and the Dolphin mine went underground from the original mine. And thanks to Tim Callaghan, who I also think I saw on the call, he led our group from the SEG UTAS into the mine this year to go poking around and have a look at what's in there. And there's some very cool things exposed. There are aplite dikes. This is from the south wall of the pit. You can even see mineralisation in some of these dikes. This is a bit of molybdenite within one of the aplite dikes. The apatite dikes are also exposed in drill holes that King Island Scheelite have done recently. So one of the interesting things that came out of looking at the core recently is that there's just a variety of different types of granite intrusion into these wall rocks. There's sort of fine-grained, more silica-rich things, there's porphyritic things, there's multi-phases, and that's kind of intriguing. So how does the mine sequence relate to all that stratigraphy I just showed you before? Now that's an interesting question. So we've got that stratigraphy lined up here on the right-hand side of this slide, and the mine stratigraphy as originally defined in the 70s by the King Island Scheelite geopico people at that time. And there's definitely some correspondences between, you know, these upper metavolcanic units and the City of Melbourne volcanics. And there's probably a link between some of the big dolomitic marbly lenses and the Cumberland Creek dolostone, but there's also a lot of question marks on here. So one of the things that I'm working on at the minute is how the mine sequence actually maps back to the regional stratigraphy as we currently understand it, keeping in mind that when this work was done, these units weren't defined. These were only defined in the 2000s. So there's a bit of work to be done to work out what's going on, especially given that these units have been well and truly skarned, as I'll show you in a minute. There are good maps of the mine pit. This is from one of the geopico geologists in 1975, and good cross-section. So this is a view into the pit, kind of along the axis that I showed you of that modern photo from a couple of months ago, looking to the east-southeast pit wall. And you can see a variety of units exposed. There's the equivalent of the Fraser Formation, which in this unit is called quartzite. There is lower metavolcanics. These are probably the Robbins Creek Formation. There's a Hornphils unit through here, which is also probably the more siliciclastic part of the Robbins Creek Formation. There are the lenses of ore, C lens, so that is most likely to be the Cotton's breccia. I'll show you that in a minute. And the skarn marble units, probably the Cumberland Creek dolostone. And then above that, there's another set of Hornfilses, probably the Yarra Creek shale. But there's another mineralisation lens above that before we get back to the volcanic. So there's, as I say, there's some things to work out about how the units relate to each other. This is from near the portal in the wall of the pit. This is the upper metavolcanic units. You can see ghost clasts within here that have been fully replaced. That's, you know, that's probably a mass flow breccia equivalent to the one I showed at the base of the City of Melbourne volcanics. Maybe, still working on that. There's a unit called the Biotite Hornphils. This is probably equivalent to the Yarra Creek shale. There's no carbonate in this unit, so it just kind of cooks up and gets a lot of biotite in it. Some of the very interesting textures, though, come from the replaced carbonate units. So this is probably the equivalent of Cotton's breccia. There are these podded diopside garnet unit pods within this unit. So these probably are old class of carbonate that have been progressively metasomatized and reacted out. So there's some really interesting textures within that. This is one of the marble units. So there's a marble with a lot of actinolite in it, but there's also more pure marble units. And then this is the C lens mineralisation itself as intersected in the core. There are sulfides and there's scheelite in here. This is a piece of waste rock that we recovered from the dump outside the pit on the grassy foreshore, and I saw Li Jun Zhang on this talk. So Li Jun brought along his magic Chinese UV lamp to King Island, and when we ran it over a bunch of the waste rocks that are dumped on the foreshore, you see quite exciting, you know, fluorescent scheelite all through these rocks, and they're significant grade. The yellowish sort of tone to the fluorescence I've been been formed is indicative of molybdenum within the shear light. And that's unsurprising, as in the pit themselves there are veins of molybdenite, and you can see pretty well exposed there. The molybdenite was never mined at King Island. This is sort of high grade ore with garnet in red and calcite skarn. So this is probably Cotton's breccia, or maybe the dolomite above it, but it's been completely reacted away to these really beautiful glassy textured garnets, calcium-rich garnets. And then under that, there's a lower metavolcanic unit. This one's actually pretty well preserved. You can see original vesicles within a lava flow. And working sort of down through the stratigraphy, I'm starting to convince myself that this might be a unit within the Robbins Creek Formation, rather than equivalent to, say, the City of Melbourne volcanics or the shower droplet volcanics, which are the upper metavolcanic sequence in the mine. Underneath those, there's the banded footwall beds, as they're called in the mine sequence. This is an example here. Again, probably the siliciclastic units of the Robbins Creek, but uncertain about that at this point. So, sort of for the last 10 minutes or so of this presentation, I just wanted to introduce some research that I've been doing in the last couple of months. So King Island Scheelite made available to us 2 drill holes, KI 064 on the eastern wall of the pit, and then another hole, KI 062, on the other side of the Sandblow Granite at a prospect called Investigator 21, that was discovered in the 70s by Geophysical drilling. So what I've done is to try and construct a cross-section between those 2 drill holes and do some geophysics to work out what's going on in the granite. Given that we saw evidence the granite is somewhat composite, I was interested in, whether the geophysics shows that whether it's uniform or not, and whether that's got anything to do with, the mineralisation. Sorry, the next slide is going to take a minute to come up. So these are 2 graphic logs that I made of the 2 drill holes that we've been allowed to access. The red bars show the magnetic susceptibility down the hole, and the black bars show the tungsten assays as from King Island Scheelite. And kind of an immediately interesting thing is that the best tungsten grades don't correlate at all with where the rocks are magnetic. And partly that's because when you think it through, the highest tungsten grades are really associated with the old carbonate units and not the volcanic units, which still preserve their magnetic signatures. So that's okay, but what it means is magnetics is not going to be a good method for prospecting for tungsten ores on King Island. This is work in progress that I've been working on. So the section at Investigator 21, I'll show you the old Geophysical drilling and cross-section in a minute, but this is their section through there. They've got upper metavolcanics, the Hornphils, middle metavolcanics, and then carbonate units, and then underneath that, what they called quartzite, but what's the Fraser Formation. And then I'm trying at the moment to work out how those things map onto the stratigraphy on the east coast that I walked you through. This is the magnetic data from the southeast of King Island. The big booming anomaly here is the volcanics of the Graham's Road volcanics. And I said offshore, you can trace them for hundreds of kilometres into Victoria, and they've got a dip thickness of about between 2 and 5 kilometres. They're significantly well developed underwater. The area of mineralisation in the aureole of the granite is in these kind of line work around here. One of the drill holes is in here. This stuff's not very magnetic at all, but what we do see is there's part of the granite, the Sandblow Granite, is much more magnetic than the eastern half of it. So the magnetics itself says that there's probably more than one intrusion here, and they've got different magnetite content. So whether or not that's significant is yet to be determined, but it's an observation. Gravity-wise, the gravity signal's dominated by the dense volcanics sitting off the coast. They have densities of about 2.9. The granite itself has a density of about 2.65 to 2.7, depending on where you measure it. It just shows up as a fairly uniform low with a gradient off to the volcanics. My mentor, Dave Lehman, who since has passed away, did some work in the early 2000s on the King Island granites, trying to sort of define the shape of the intrusions underneath the island. It's a pretty coarse modelling job, but one of the things he thought was indicated by the gravity data was that what he called the grassy granite diorite, now called the Sandblow Granite, had pretty steep margins. So you see the isobaths here clustering together, indicating a very steep eastern margin and a very steep western margin to the granite with a bit of a plunge off to the north. But that was all very coarse work, so that's never been verified since by any sort of more detailed follow-up. This is the cross-section from the GeoPico geologists who GeoPico owned King Island Shear Light, and a certain Ross Large, I believe, was the exploration manager for a time in the early 1980s. This is their percussion drilling and one or two diamond holes through this prospect called Investigator 21. And they went through a series of rocks here and then into the granite underneath, which they're showing as dipping away to the west, but then sort of question marks all over it. Where does the granite go? Did it come back up? Did it go heaving down? I guess that's an important question, because if there's a lens of ore through here that they've defined, you know, if there are repeats of the stratigraphy and the granite keeps going down, is there more potential for mineralisation in the blank spaces? Or if the granite comes up, has it been totally removed? So the question is, where does the granite go? And what I've done is create a cross-section from Investigator 21, so that's that drill hole KI062, to the west through to the Grassy Mine KI064 into the east, and then out into Bass Strait. This is the gravity from that area, so generally showing a gravity low over the granites like we said. And this is the magnetic signature, and what we see here, unfortunately, it's kind of dominated by the volcanics to the west, but even without those, there's a significant 200 nanotesla anomaly over part of the Sandblow Granite and not over the eastern part of it. So that's that high-low pair that we saw in the magnetic image. And what that tells you is there's a contrast between two parts of the Sandblow Granite, possibly two different intrusions. They have a pretty steep contact that you need to match this gradient here. And like Dave Lehman's modelling, I'm showing a very steep fall off on the granite underneath the Fraser Formation. So the granite really is steep on its edges. That cross-section through this area is basically controlled by the GeoPico work. So we've actually modelled all of their units in that piece of pendant of mineralisation in there. This is the main area where the Dolphin Grassy Pit and the Dolphin deposit are. So you can see that, you know, within a small roof pendant block, you had a world-class mine. There's probably no reason to suspect that you couldn't get a similar world-class resource out of a piece that's about this big, given that you've got the same sort of intrusive things going on underneath. And they definitely intersected mineralisation in these holes, but it was never really followed up. Just a few more observations before I close out. Just supporting the idea that the Sandblow Granite might be a multiple or composite intrusion. The radiometric data are quite interesting. There's a very high potassium and uranium rich part of the Sandblow Granite down here on the south coast at a place called Crown Creek. It really lights up compared to the rest of the granite body, which is pretty muted in its total count radiometrics. And this is the uranium and thorium channels as well. So the I guess for an I-type granite, you're not surprised that it doesn't have really high uranium. That's probably more an association with S-type granites. But nevertheless, there's some evidence both in these channels as well that there's probably another different kind of intrusion down here with a different mineralogy. Whether or not that's significant, I don't know yet. So to close out, observations there, Sandblow Granite, probably a composite body. It's got magnetic, non-magnetic phases. It's got radiogenic and less radiogenic pieces. The dikes that I showed you from the drilling also have quite variable composition. So there's obviously quite a bit of an evolving magmatic story there that's yet to be unravelled. I haven't seen anything in the literature about sort of multiple intrusive events. So that's something I'm sure the guys at Codes will work on. There's evidence that one of the granite bodies is a bit denser than the other. So maybe it's a bit more mafic or a bit more I-type than the other piece. Interestingly, the Sandblow Granite is less radiogenic than the basement that it intrudes. From the modelling, we can see that the dense skarns are they're depth-limited pendant blocks. They don't really continue to depth. They're cut out. They don't have really strong gravity signatures that give them a chance to be really extended at depth. But despite that, obviously, the piece at Grassy hosted a world-class mine, and Investigator 21 may be a significant resource in the future. The granite itself, as I said, has steep culminations, and I'm sort of working and talking to people about whether or not any of this has got any influence on what actually controlled the tungsten deposition originally. And so that's a wrap for a walk through King Island geology, a bit about the mine, a bit about the geophysics regionally around the mine. Thanks for listening to my AIG talk. And I'd like to thank a few people before I close out. Clive Calver, Paul Hoffman and Jim Jago for all their discussions with me about King Island geology and sort of sorting out all of the pieces of the stratigraphy. Lee Jeune and Dave Cook for getting me excited about skarns. The UTAS SEG chapter for taking me back to King Island a couple of months ago and getting us into the mine to look at all those exposures there. Tim Callaghan and King Island Scheelite, especially thanked for letting us look at the drill cores and allowing us into the mine. Shelley Greener suggested that I give this talk and she collaborated and connived with Jane to make it work. And I'd also like to thank MITRE Geophysics people for giving me time out to work on some research. Thanks, everyone.
That was fantastic, Nick. Thank you. And I must admit, I really appreciated seeing such a wide range of rocks in one spot with your photo collection. So absolutely unreal. Obviously, if you'd like to ask a question, everyone, you can now. You should be able to unmute yourself if I've set the settings correctly. So dive in and ask Nick a question if you like. Here we go, Douglas.
Yeah, hi Nick, this is Doug Kerwin. That was a really great talk and it's wonderful to see so many rocks and slides of the geology. Given the size of the King Island tungsten system, has the smoking gun actually been found anywhere? One would think that there's a highly fractionated intrusion in there somewhere, and other than the uplight dikes, there doesn't seem to be much evidence for it yet.
Yes, I mean, I haven't by any means looked at all the drill core that's available. And, you know, what's actually exposed in the pit doesn't look super fractionated, although I see Dave Cook on the call. He might care to chime in a minute with what he observed when we were there. But I think as we get to grips with some of the older drilling, you know, finding the old drill cores from GeoPico is a bit of a hit and miss thing. One of the holes, DDH68, that I didn't really show much of, had lots of different phases of granitic things in it, and some of those might turn out to be quite fractionated, I guess, if they're sampled. But I'd say that's work to do. It's a bit outside my expertise. I'm not a granite geochemist by any means, but you know, it's something that that people might go hunting for. And I guess the key thing that I'm interested in is if we can find a highly fractionated granite, is there some geophysical signature that goes with it so that we can track it around in southeast King Island and try and work out where the juicy bits are?
Okay, thank you.
My understanding that there's when the Shear Light mine shut down back in the 80s, they made a library of core that they, I can't remember the mines department where they put it, but there was a library of core made up. Are you aware of that one?
Yes, yeah. Nick Turner, who was contracted to MRT, certainly catalogued a lot of the core and the drill logs and things. And they are kind of available through the Tiger database, but I think, unfortunately, in the process of getting the cores from King Island down to Hobart to the Mornington core store, some things have gone missing. People made choices about, you know, what we should keep and what shouldn't be kept, and things got thrown out. So it's a bit of a, there's a bit of a detective work to be done to kind of go and find the key bits of drill core that still exist and work out, you know, what they mean. But yes, for sure, there are drill cores at MRT from GeoPico's time. Yep, and I've looked at some of them.
John Bishop here, Nick.
Hey,
I noticed Steve and Mudge is in the audience, and Steve many years ago wrote a rather interesting paper suggesting that King Island came out of Macquarie Harbour, and I wonder if he still holds to that possibility, and if so, whether you've got any comment on it.
Well, it's interesting you say that, because Mr. Mudge actually sent me a copy of his paper a couple of weeks ago, along with a very interesting cartoon from his time working at GeoPico. I won't comment what he believes, but I will comment from the point of view of the more modern magnetic data sets that we have, including the offshore marine data that I've worked on extensively, and kind of reconstructing things back into pre-rift, you know, pre-Antarctic breakup sort of configurations, pre-Cretaceous. I'm fairly convinced that King Island doesn't come out of Macquarie Harbour, but it does come from, there's a huge fracture zone to the west of Tassie, the Sorell fracture zone, and it looks like it's been translated along one of those type of structures to its current location during the rifting that happened in the Cretaceous. So it's come from elsewhere, and that's kind of encoded in the rocks, right? There's bits of Antarctica in King Island that don't really exist much on mainland Tasmania, so they've got to have come from somewhere else. So it is a bit of a detective story, but I'll let Steve add his own comments if he wishes. It's gone quiet. You might have to grab a beer.
As you noted earlier, I did my honours thesis on the other side of King Island, and you know, I'm a lot older now than I used to be then, but one of the zones between Fitzmaurice Bay and Fitzmaurice Point and Surprise Bay, there's all these sort of myelinised, I don't know what it was, but I was just wondering if you stomped on any of those rocks to the south of Fitzmaurice Point, and whether you had any observations from them.
No, I haven't spent a lot of time on the west coast. Probably the most time I've spent down there was this April, when we spent a day traversing the outcrops there, looking at the different generations of folding. No, I don't have an opinion. The people who know the most about that will be Clive Calver and John Everard, who mapped it for MRT. And there are new maps. So if you go onto the MRT website and download the Stokes map sheets at 1 to 25,000, you'll certainly see the new mapping. So that might give you an insight into the current understanding of what's going on down there.
Hey Nick, I've got a question for you about the bold head adamelite versus the grassy granodiorite that you showed on the old map, and the offset of those.
Yeah.
In the fault offset between those, when did that occur? And have you got any feel for the throw and how that fits into the story?
Yeah, so the Grassy River Fault is the fault that's believed to offset the bold head piece of the granite from the rest of it. That fault was intersected a lot of times by the old underground mining operations and things. I don't think anyone's ever dated anything out of that fault, material. It's obviously post-Devonian or post-Carboniferous, but I'm not entirely sure whether it would be to do with the Bass Basin rifting in the Cretaceous. It could be just a late, post-Carboniferous thing, but there's not a lot of tectonic events to kind of choose from after intrusion of the granite. So if we went back to that tectonostratigraphic column between intrusion in the Carboniferous and Quaternary, there's basically Bass Basin happens, and that is a lot of faulting. Like there's no doubt, you've made a huge hole in Bass Strait. A lot of things going on there. King Island became a high block, so maybe at that point it could have been faulted, but I don't know what other options you've got. And also, as I said, I don't think anyone's dated anything like fault gouge minerals or anything out of what has been intersected in the drilling to say, okay, yes, we think it's Cretaceous faulting, or it's Permian faulting or something that hadn't been recognised.
It seems to have a pretty serious throw on it as well, though, Nick. So it looks reasonably substantial.
It does, and wouldn't dispute that.
Yeah. All right. Thanks.
All right. Well, we're kind of well and truly over the time contract that we had with you all. Nearly 7:10. So thanks for hanging around and listening, everyone. But if there's a last question, quickly throw it out, or I'm going to throw it back to Jane and let her wrap things up.
Doesn't sound like. Oh no, here we go.
I was just going to say I'm very pleased to see there's Glenn Neves in my top left hand of my screen wearing high vis, so it looks like he's in a mine office somewhere and listening to the talk. So that's all great.
Well, it was a very quick hour. There you go, Nick, because it was so interesting. So time flies. So thank you very much again for your time. And I know pulling these things together takes a lot of effort. So we really appreciate that. So lots of gratitude from AIG Tasmania. And I'd like to thank everyone who came along as well from all over the place. It's our first event like this. So thank you for bearing with me, since I've never used Zoom in such a big crowd before. So I think it's gone okay, and we'll get the recording up so everyone can watch.